Oh, gotta have my favorite student. Number one, the key word that I see is the word orbit. As soon as I see the word orbit, I can say to myself, gravity is what's pulling me in a circle. Gravity is what's pulling me in a circle. And from here, I'll derive whatever I need to derive. The gravitational equation won't change. It's going to be big G, big M, little m over r squared. The circular motion one is going to be MAC, but I need to decide which version of AC I want to use. Since they mentioned speed, I'm going to use v squared over r. In this particular version, an m cancels. In this version, an r cancels. And I end up with orbital speed ending up being the square root of big G, big M over r. It's going to be the square root of 6.67 times 10 to the negative 11. Are we around the Earth? Yep. 5.98 times 10 to the 24th divided by, is this in meters? Yes, it is. 8.1 times 10 to the 8th. Do I need to add the radius of the Earth to this? Do I need to add the 6.38 times 10 to the... Now, when would I, if instead of saying orbital radius, if I had said altitude or height, then I have to add the radius of the planet. But here I don't. Those of you that have the hot button keys for the big G and mass of the Earth, you might be different on our third or fourth sig fig, but we should be the same to two sig figs. 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24th divided by 8.1 times 10 to the 8th square root. Answer button. You get 701, 702? Is that right? If you got that right, 2 out of 2. Otherwise, I would probably do something like this. I would give you a half mark if I saw gravity is pulling us in a circle. I would give you a half mark for that. I would give you a half mark for that. And I'd give you a half mark for the answer. B, what's the kinetic energy? Oh, easy peasy. Ke equals a half mv squared. It's going to be 0.5 times 2,500. Oh, that's why they gave me the mass. Times 702 squared. I wrote 702, but you know I'm going to use my answer button. 0.5 times 2,500 times answer button squared. You get 6.16 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8. Is that right? Joules. Mr. Dueck, yeah, Nino. I thought you said that when we were in orbit, usually we were in the 10 to the 9th or 10 to the 10th range. We are really far out. We're 10 to the 8th out from the Earth, from the center of the Earth. Our orbital speed is really slow because we're really, really far out. We're far removed from Earth's gravitational field. We're still in it, but not by much. And so we don't need as much kinetic energy. Okay. For 2 marks, I don't know. 1 mark for that. Half mark for that, half mark for the answer. If you got 1A wrong, but you went a half M, whatever your answer from part A squared was, and you did that correctly, I'll give you 2 out of 2 for part B. Again, the key word here, Johnny, orbits. So I can again start out by saying gravity is what's pulling me in a circle. And I can say big G, big M, little m over r squared equals m. Since it's talking about period, I'm going to go 4 pi squared r over t squared. Again, little m cancels. They want the orbital radius. I think here I'm going to get r cubed equals big G, big M, t squared over 4 pi squared, I think. And then how do I get rid of a cubed? Cube root. Oh, boy. Nice to use the cube root function for a change. I'm kind of running out of room to right, I would, big G, 6.67 times 10 to the negative 11. Earth, 5.98 times 10 to the 24th. Well, let's keep going, Mr. Dueck. Big G, 6.67 times 10 to the negative 11. Big M, 5.98 times 10 to the 24th. T, 2.4 times 10 to the 4th squared, divided by 4 pi squared. And then I want the cube root of that. For me, it's math option 4, answer button. You get 1.7, I guess 1.80 if I round off properly, times 10 to the 1, 2, 3, 4, 5, 6, 7. Is that correct? People nodding? Okay. 2 out of 2 if you got that. Otherwise, same as before, I would give you a half mark for that, a half mark for that, a half mark for the cube root equation, and a half mark for the answer. What's the gravitational potential energy of this satellite relative to 0 at infinity? What does that last phrase mean? I'm saying, Victor, make sure you use the cosmic potential energy equation. Don't use MGH. So this isn't a change in, this isn't asking how much work, this isn't a conservation of energy. This is just going to be straight plug and chug. The gravitational potential energy is going to be negative big G, big M, little m over R. Now R is going to be my answer from part A. It's going to be negative 6.67 times 10 to the negative 11, 5.98 times 10 to the 24th, mass of the satellite, all over, I'll write 1.80 times 10 to the 7th, but I'm going to use my answer button here. Negative 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24th times 1200 divided by answer button, not squared. Squared would be if they wanted me to find the gravitational force between the Earth and this particular satellite. And I get negative 2.66 times 10 to the negative 10, Mr. Dueck? Oh, I missed. Arg. Okay, this is going to be yucky. My power of 10 is wrong. I think it's to the positive 10. I missed the 2 in front of the 4, yes? It's negative 2.66 times 10 to the positive 10? Yes? Okay. Joules. 3 marks if you got that, 3 out of 3. Otherwise, I would give you 1 mark for the equation, 1 mark for the numbers, 1 mark for the answer. Why negative? Here's what this is telling you. If you wanted to get this satellite completely out of Earth's gravitational field, you would have to add that much more energy to get it to 0. You would have to figure out how much rocket fuel you needed to add positive 2.66 times 10 to the 10th joules to this number, and that would allow you to escape the Earth's gravitational field. And we're going to look at that later on today. We're going to use it to calculate escape velocity. Number 3, how much work? Now, we are lifted. We are not in orbit. And I also noted that this question gave me an altitude. My first thought was, well, work equals force time. No, I can't go force times distance because the force is changing, because gravity changes as you move further out. What happened to the change in kinetic? Because we're not in orbit, I can do that. Now, on your test, I'll probably put you in orbit and do the full schmeal. But okay, so change in anything is going to be final, negative big G, big M, little m over R final, minus negative big G, big M, little m over R initial. I do get a minus minus, which is a plus. Yay! It's going to be negative 6.67 times 10 to the negative 11. Earth, 5.98 times 10 to the 24th. 6,450. 4.6 times 10 to the 5th. Do I need to add the radius of the Earth to that or not? Yeah? Why? It's an altitude. Also, because if that was the radius, I'm underground, because the radius of the Earth is 10 to the 6th, 6.38 times 10 to the 6th. So I kind of know that I'm not going underground, plus 6.38 times 10 to the 6th. Minus is a plus, ditto mark times ditto mark times ditto mark divided by 6.38 times 10 to the 6th. Again, if you want to type that in one fell swoop, you can. I find it way easier to backspace and edit. It's going to be negative 6 point... You know what, Mr. Dueck? Why don't you bring back this last one here? And then there's your 24 times 6,450. That was less typing. Divided by bracket 4.6 times 10 to the 5th. Plus 6.38 times 10 to the 6th. And for the final, I get negative 3.7612 times 10 to the 11th. Negative 3.7612 times 10 to the 11th. Plus. Is that right, Mr. Dueck? That looks okay. And then the initial, I lose the negative. And I lose this. I get positive 40324 times 10 to the 11th. 4.0, what did I say? 4.0324. And final answer, that number plus negative 3.7612 times 10 to the 11th. This time I'll check for typos. Looks good. Do you get positive 2.71 times 10 to the 10th joules? No, yes? Yep. So if you got that, 4 out of 4. Otherwise, I would probably go something like this. I would give you 1 mark if I saw that. I would give you 1 mark if I saw that. I would give you a half mark for that number and a half mark for that number because it is a lot of typing. And then I would give you 1 mark for the answer. Probably something like that. If you could give yourself a lovely score out of 13, that would be wonderful, please. I called this lesson, Sean's going to put his phone away, I called this lesson Orbital Mechanics. First of all, suppose a mass little m, let's make it a rocket, is moved from the surface of a planet to a distance big R from the planet's center. Which of the following is true about the work done? First question, does this question mention the word orbit at all? Okay. Thomas, how would I figure out the work? You answered this question on the quiz, not... Better yet, what's changing anything? So it's going to be negative big G, big M, little m over, they're calling our final big R, so I'll use their notation, minus negative big G, big M, little m, and it looks like the initial radius is little r. Well, I'm looking here, which of these is correct? A, B, C, D, or E? Nina? D? Oh, minus is a plus? Okay. What's wrong with A? Why can't I go force times distance? Because doesn't that work? Yeah, force is changing, unfortunately. That's why I told you way back when I gave you the work energy theorem, it's a much more useful definition of work, even though it's much more cumbersome. Yeah. Okay. These ones here are various ways. You could maybe factor out a big G, a big M, and a little m and write it with a common factor, but I've never bothered doing that. It doesn't make it all that much better, especially if we choose to just backspace and go with ditto marks. I think that's the fastest approach here. And so, yeah, none of these work. Explain your answer. Okay. Yeah. I really want to talk about escape velocity. It should be called escape speed because it's a scalar, but in the industry, the jargon that they use, they do call it escape velocity. So, Jacqueline, I'll call it that. Here's what it asks. How fast do you need to go away from a planet before you can just shut your engines off and coast the rest of the way to the edge of the universe? How fast do you need to go to completely escape a planet's gravitational field? That's escape velocity. So to escape from a planet's gravity means, in theory, to travel an infinite distance from the planet. In reality, it means to travel far enough away from the planet that the pull of gravity has become really small, negligible. Negligible. To barely escape would mean to escape from a planet, so you fire your engines all at once and you hit your escape velocity, and now you shut your engines off. You're coasting away from the planet, but the planet's still pulling at you, so you're slowing down, you're slowing down, you're slowing down, you're slowing down. To barely escape would be to do it so perfectly so that right when you reach the edge of the universe, James, that's when you come to a stop. That would be doing it perfectly with no wasted energy. You follow that? So to barely escape means to escape from a planet with no kinetic energy left at the end. So you end up at rest and at an infinite distance. Escape velocity asks, how much kinetic energy is required to bring potential energy to zero? Because out of infinity, that's how much energy I have. And we can find it using conservation of energy. Looks like this. I think we'll write one line on this page. KE initial plus PE initial equals KE final plus PE final. Now, final is out at infinity. How much potential energy do I have out at infinity? Exactly as a number. Zero. We defined it that way. We've defined this equation so that when r, by the way, those that are in calculus, if you take the limit as r approaches infinity, you do get an infinity in the bottom of your fraction and you get zero potential energy. That's a little calculus thing there. So this here equals zero because we defined it that way. And what we're saying is we want to come to a stop when we get to infinity. So how much kinetic energy do I have at the end? And so what I really strangely end up with is this. KE initial plus PE initial equals zero. I'm not saying that I have no energy here. I'm saying how much energy do I need to start with so that the negative potential and the positive kinetic perfectly cancel out and I end up with nothing left over. Kinetic energy is a half mv squared. Potential energy, are we cosmic here? Can we use mgh? No. Is going to be negative big G, big M, little m over R initial. That equals zero. You okay with that, Thomas?
Why are we using R initial?
Because this is PE initial, and I'm having used cosmic. Okay. What's right in front of the PE? Negative. You know what? I'm going to plus it to that side, and I get this. A half mv initial squared equals negative big G, big M, little m over R initial. Oh! Turns out the escape velocity for the space shuttle will be the same as the escape velocity for a little cube satellite. Doesn't matter how big your object is. Once it gets to that correct speed, it can shut its engines off. And now, Nina, we want to get the V by itself. I think... Oh, sorry. Thank you. That's what you were staring at. You're right. Thank you, Nina. Candy for you. And then, Nina, if you don't mind, I'm going to go times by 2 to get rid of the 1/2. And that gives me VI squared equals 2 big G, big M over R initial. How do I get the V by itself? This is your escape velocity. Now, here's what this is saying then, Sean. This is saying, here's how fast you would need to leave a planet if you know the planet's radius and you know the planet's mass, that's how fast you need to leave, and then you can shut your engines off and coast the rest of the way. So we get this. V escape equals 2 big G, big M over R initial square root. By the way, compare that to V orbit, which was just big G, big M over R square root. It looks like escape velocity is root 2 times as big. I don't believe I put this on your formula sheet, did I? And I don't think I needed to because we derived it from conservation of energy. I will be asking you an escape velocity question on your test. Okay? And big G, 6.67 times 10 to the negative 11. M, mass of whatever planet we're talking about. You want to find the escape velocity from the sun. You want to find the escape velocity of Mars. You want to find the escape velocity of Jupiter. Done. And R would be how far you're starting from the planet's center. If you're starting on the surface, R initial will be the surface. But you could also be already starting at a given altitude. We could figure what that radius was. You've already got out of the Earth, the planet's gravitational field somewhat. One of the things we'll look at is escape velocities from black holes. And believe it or not, this equation right here is going to allow us to derive some information about black holes. But example 2 says this. Find the escape velocity for the Earth and for the Moon. Okay. It's going to be the same procedure for both of them. Now, you can choose to commit this to memory if you want, or you can derive it. Since we have it sitting in the box, I'm not going to derive it this time. I'm going to go straight to V escape equals the square root of 2 big G, big M over R. It's going to be the square root of 2, 6.67 times 10 to the negative 11, 5.98 times 10 to the 24th, all over. We'll assume we're starting from the surface of the Earth. What is the Earth's escape velocity? How fast do you need to be going? I have this one sort of half memorized because it's almost 11,111. Like it's almost 5 ones. It's not quite, I think, but I've always remembered it as it's nearly 11111, and my brain can remember that. You get 11,000 something. What'd you get, Dylan? So 11,200. About 11 kilometers a second. We do that. We've done that. We can accomplish that with our current level of technology. The Apollo rockets did that. They actually went fast enough so that they could shut their engines off and coast to the moon, but it was a bit more of a complicated equation because also the moon was pulling them in. But yeah, we've achieved escape velocity. Our probes that go to other planets and other celestial bodies, they achieve escape velocity. Do you think the escape velocity from the moon would be bigger or smaller than the Earth's? Smaller? Why? What would make it? Why? And smaller gravitational field? Yeah. Okay. So same numbers here, except I have to use the moon. Sorry, not same numbers. Same equation here. It's going to be 6.67 times 10 to the negative 11. I have no idea. What's the mass of the moon? It's on your sheet. I think it's 7 point something. To the 20. And radius of the moon? What's the escape velocity from the moon? I know it's going to be less than 11,200. What do you get? Yeah. Oh, I forgot the 2, Dueck. I'm doing orbital speed. I'm in a slump. Boy. Do I want to put this video on YouTube? Yes, I will, so that my students out there can see that I make mistakes all the time. I should model what I practice. Mistakes are good. We learn from them. What'd you get? This one I don't know. I just know it's less than 11,000. Michael, what'd you get? So 2,370? 2370? Yes? Okay. And that one we did when if you watch the old Apollo footage, when they left the moon, they had to get away from the moon and leave. 2,370 meters per second. Of course, it's possible to reach infinity and still be moving. You could have extra kinetic energy. That equation would look like this. A half mv initial squared plus negative big G big M little m over r initial equals a half mv final squared, plus 0, because out at infinity your potential energy is still 0 because there's no gravity tugging on you. But okay, you might have some extra speed to burn once you get there. Oh, and again, doesn't matter how big your spaceship is. Now, if we were calculating how much energy, how much work was required to do this, then the m's wouldn't cancel. And I really should have said, instead of that work equation, I should have said that energy equation would look like that, I guess, technically. I'll have to fix that. Let's look at black holes. They're pretty cool. Suppose a spaceship is 8.5 times 10 to the 9th meters from the center of a black hole. The black hole has a mass of 50 times that of the sun. What's the gravitational field strength at that location? What symbol or letter are we using for gravitational field strength? Uppercase or lowercase g? Because that makes a big difference. Uppercase G? I know the answer. It's 6.67 times 10 to the negative 11. I don't think that's the gravitational field strength. That's the universal constant that we have to use to get our answer in newtons. Big G is not our symbol for gravitational field strength. What's our symbol for gravitational field strength? Now, little g, put your pencils down, look up. In Physics 11 and in Physics 12, I always said to you, get the obvious one. What did I mean by that? Whenever I said get the obvious one, what two letters did you write on your free body diagram? Okay, so we have this idea here. Do me a favor, Maddie. Get little g by itself. And that's the third equation that I gave you on your sheet, yes? Except now, are we going cosmic here, Nina? Then this Fg needs to be this equation. Do you see how I turned that into that? And what do you notice happens? This is the equation for gravitational field strength. It's big G, big M over R squared, no little m. I deliberately did not give you this equation on its own. I gave you this one because I want you to realize that gravitational field strength is force divided by mass, because it's also another way to measure acceleration. Having said that, then, how big will it be here? Big G is 6.67 times 10 to the negative 11. M, it says it's 50 times the mass of the sun. So 50 times, mass of the sun is on your sheet. I think it's 1.98 times 10 to something. Times 10 to the 30? Divided by 8.5 times 10 to the 9th squared. We're talking a black hole. Maybe we'll have a big gravitational field. I don't know. What'd you get? Really would encourage all of you to practice typing these in. Get that? Roughly 9 times Earth's gravitational field. Just about 9 Gs. Could people in that spaceship survive it? Well, if you're in orbit, how much of that gravitational field would you feel? You'd be in free fall in orbit, and so you actually wouldn't feel this at all, okay? You would just feel floaty. Coming into orbit, you might notice it. Once you were approaching, it'd be kind of weird on your body, but once you were there, it'd be just like orbiting the Earth. 91.4 units for gravitational field strength. If you said meters per second squared because you treated it as an acceleration, I'm okay with that. But from here, what should the units be? What do I measure force in? What do I measure mass in? That's another way to write acceleration, but whenever I'm talking about a gravitational field strength, I'll almost always use those units. That many newtons of force on every kilogram of mass. How fast would the spaceship need to travel in order to escape from the black hole's gravity well? We want to find escape velocity, which we start out with kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. It's a conservation of energy question. And again, it should be called escape speed because speed is a scalar coming out of here, but they call it escape velocity, so okay. To escape, what do we want our final potential energy to be? And to do it with a minimum amount of fuel, just perfectly, what do we want our final kinetic energy to be? And so what we really end up with is a half mv initial squared plus negative big G, big M, little m over R initial equals 0. We end up with a half little m VI squared equals big G, big M, little m over R initial. Right around here we can smile. We could have canceled out the m on this line, I guess, but little m's going to cancel. And so the escape velocity, we need more room, Mr. Dueck, is going to be the square root of 2 big G, big M over R. So it's going to be the square root of 2 6.67 times 10 to the negative 11, 50 times the mass of the sun, divided by 8.5 times 10 to the 9th, not squared. I'm actually going to try and backspace, and I'm going to see if, because this has all the numbers that I want, I'm going to insert 2 times right there. And then I think I just need to delete the squared right there. And then square root of that, I think. Double check me, but I got 1.25 times 10 to the 1, 2, 3, 4, 5, 6. Yeah. C. How far away from the black hole is the event horizon? Now, what do we mean by the event horizon? That's the point where if you're closer than that, nothing can escape. If you're further than that, it's still theoretically possible to escape the black hole. What speed would be crucial in the event horizon? First of all, how far away? What's this question asking me to find? What we're going to do is we're going to use the escape velocity, and we're going to let escape speed equal c. Who remembers from Physics 11 what was lowercase c an abbreviation for? If you let your escape velocity be the speed of light and solve for r, that will tell you where the black hole's event horizon is. Anywhere closer than that, nothing in the universe is getting out. Anywhere further than that, now if you're 2 meters away from the event horizon, your escape velocity is probably 99.999999999% of the speed of light, so you're still probably out of luck. But this is where, if you were observing a black hole, you would see a ring of weirdness and stuff being swirling around and spiraling around. So let's find this. So V escape equals the square root of 2 big G big M over R. What's the R inside of that I don't like? Oh, how about we square both sides? We get this. V squared equals 2 big G big M over R. Michael, what are we trying to find? Where is the R right now? Ugh. Oh, wait a minute. Let's multiply it to there and divide the V squared there. And we're going to get this. R equals 2 big G big M over V squared. This will tell you where the black hole's event horizon is. It's also called its Schwarzschild radius. 2, 6.67 times 10 to the negative 11, 50 times the mass of the sun, divided by, what was the speed of light? I think I put that on your formula sheet too, didn't I? Okay. 3 times 10 to the 8th squared. I'm kind of curious. Do you get, wow, worked out evenly, I'll take that. Do you get 146740? Or am I wrong? Okay. 1.47 times 10 to the 5th meters. Okay. Example 4. I like example 4. I like example 4. I like example 4. Mr. Dueck. Oh, you got a lot more to try and cover. You got 20 minutes left. We'll finish with example 4 for now. Okay. Samira, what's example 4 wanting me to find? Find the... Oh, this is easy. Force times distance, right? Oh, am I going to have to use the work energy theorem? Are we in orbit, Thomas? So I can't just cross out the K. Oh, jeez. I recommend, Samira, finding each of these separately. Which one do you want to find first? Change in potential or change in kinetic? Okay. That's going to be negative big G big M little m over R final minus negative big G big M little m over R initial. I got a couple of problems here. This number here, why don't I like the 25,500? What's yucky about it? Kilometers. Okay. 25,500 times 1,000. And I get 2.55 times 10 to the 7th. Is that a radius or an altitude? Someone said altitude, someone said radius. From the center. Now, I was sneaky because the picture makes it look like an altitude because of that little line right there. but from the center. It is a radius. Okay, so here we go. It's going to be negative 6.67 times 10 to the negative 11. 5.98 times 10 to the 24th. 12,500 kilograms. Our final, it's 2.55 times 10 to the 7th, and I'm not adding the radius of the Earth to that one because that already is a radius, not an altitude. Plus, same thing times same thing times same thing divided by 6.38 times 10 to the 6th. Type that first one very carefully. Negative 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24th times 12,500, Mr. Dueck, divided by 2.55 times 10 to the 7th. I get negative 1.9552 times 10 to the 11th. Plus, I didn't want to do that, Mr. Dueck. There, I brought it back. Okay. Delete the negative. 6.38 times 10 to the 6th. 7.8148 times 10 to the 11th. So this plus negative 1.9552 times 10 to the 11th. I get a change in potential of 5.8596 times 10 to the 11th joules. And Samira, I'll put a box around that because I ain't done. Is that right? Can anybody else get the same thing? Michael's nodding. Two of us. William? Okay. Because it is very easy to make a typo. What's the next thing I need to find? What's changing anything? So it's going to be a half m v final squared minus a half m v initial squared. Now, we decided last day that we would be launching from Superman's Fortress of Solitude on the North Pole, and so we can say we have no initial kinetic energy, because if you launch from the equator, you're spinning faster, and you do have but then I need to know what latitude you're at if I wanted to include that. So we're going to go launching from the North Pole. How fast am I traveling? Did they tell me? Did they say the word orbit? Gravity is what's pulling me in a circle. Big G, big M, little m over r squared equals m v squared over r. Little m cancels, yes. One of the r's cancels. And then, Samira, I was going to take the square root, but then I said, wait. Isn't there a squared on this v here too? Then you know what? V squared right here is big G, big M over R. I'll just replace it in there as a temporary holding. I guess the change in kinetic energy is going to be a half little m, big G, big M over R. Okay. Well, now it's kind of plug and chuggish. The change in kinetic energy is going to be 0.5. Little m was 12,500. Big G, 6.67 times 10 to the negative 11. 5.98 times 10 to the 24th. Divided by, which R? Oh, if it's V final, I'll bet you it's R final. Yes, for V final. So it's going to be the, what was it, 2.55 times 10 to the 7th. Point 0.5 times 12,500 times 5.98. No, times, geez, Dueck. 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24th divided by 2.55 times 10 to the 7th. This, by the way, is the single longest question of the year, where I ask you to find how much work, and I don't give you the speed, I just give you the radius. Or I could just give you the period, which you could use to find the radius, because if you know one, you know the other. I got 9.7761 times 10 to the 9.7761 times 10 to the 10th joules. Are we done? No. Samira, what did this question want us to find in the first place? Which was going to be change in potential, 5.8596 times 10 to the 11th, plus change in kinetic, although I'm going to use my answer button for that one, plus 5.8596 times 10 to the 11th. This is a lot of work. And I wish that was a joke. No, this is just a lot of work. 6.84 times 10 to the 11th. And that's joules. Okay. Get the same thing? Anybody else? I should have asked if got one thumbs up. Anyone else? Couple? Okay. Because there is, as you can see, a lot of room to make a typo or to copy a number down wrong or to mix up an altitude, whether it's an altitude or a radius. Oh. I'm going to be giving you a lot of questions for homework. If you want to get a head start, questions that you're capable of doing right now. Number 1. And it says write a work energy equation. I would write a conservation of energy equation. And when it says at what point will it stop, I guess KE final will be 0. Solve for R final. Try number 2. I think I'm just going to assign those two for now. Put your pencils down, look up.